Hello, Algebra 2. Welcome to Chapter 9, our last chapter of the year, though this is probably the most important chapter for anyone going forward. We're going to be building on what you guys did in geometry with the sine, cosine, tan, and also your special triangles. We'll do a little bit of review of that in this lesson. So a couple things I want to say. You're going to always need a calculator handy. And that calculator should be in degree mode. So there should be a button that says either DRG or DEG, and you want to make sure you toggle through that so that you see maybe a DEG on your screen. If you have a grapher, you're going to find the key mode, and underneath that key it'll have your choice for radians, degrees, because right now we're going to do degrees, later on we'll be doing radians. All right, and you might want to have some scratch paper, and definitely take advantage of, since this is a video, pause when you need to, maybe even back up a little and replay, but definitely maybe pause and try some of the examples on your own as we work through this. All right. So let's get into it. So right triangle trig, obviously that means we start with a right triangle, and we always label, remember, the vertices with a capital letter, which means the side opposite that would get the lowercase letter. So those are just sort of our standard for how we label a triangle. And when you're doing your trig, I'm going to assume you guys remember nothing. So when you're doing your trig, it's all about what angle are you standing at? What's the angle you're talking about? And theta is a very common Greek letter that we use to represent, as you can see, I've done it down here. That is your Greek letter theta. And we often use that to represent an angle. So I'm here at angle A. Because I'm standing at angle A, that means that little a here represents the opposite side to angle A. Side C is opposite the right angle, so that is always the hypotenuse regardless of whatever angle you're standing at. That leaves side B as our adjacent. It is adjacent to angle A, so all of these are relative to a specific angle. And then the trig that we have is basically a shortcut to represent a ratio of two sides to that particular angle. So when I say sine angle A, and again this is an abbreviation, SINE, the sine of angle A, what does that represent? That represents the opposite, whatever's on the opposite side, so in this case that would be little a, to the hypotenuse, which is C. And if I said cosine of angle A, and again that's an abbreviation, the cosine of angle A, that is an abbreviation for saying look at the ratio of the adjacent side, which is B, to the hypotenuse, which is C. And lastly, we have the tangent of angle A, and so tan is an abbreviation for tangent, and that represents looking at a ratio of the opposite side to angle A. So you always have to go through the triangle to get to that opposite side over the adjacent side. Notice that the tangent has nothing to do with the hypotenuse. So those are the three ratios that you guys learned last year, and you learned that nice little acronym SOHCAHTOA, which basically means sine is opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent. What you're going to learn this year is each of those ratios has a reciprocal ratio. So these are called your reciprocal functions, or your reciprocal identities. So if I took sine and switched the opposite and the hypotenuse, you get what we call the cosecant. This is how you would spell it out, but we abbreviate it CSC. So the cosecant of angle A is the hypotenuse over the opposite of angle A. So those are reciprocal functions. Then you have the cosine, which is adjacent over hypotenuse, and if you switch those, you get what we call the secant, and that's going to represent the hypotenuse over the adjacent of angle A. And lastly, we had the tangent, and if you reverse that order, the cotangent of A is the adjacent over the opposite. So this is an abbreviation of cotangent. And all these names that look very similar to each other, there's meaning behind that, which might not come out until a little bit later. But you are going to want to learn which ones go with which. So I tend to always write them in the same order: sine, cosine, tan, cosecant, secant, cotangent, so that you have the reciprocals right next to each other. Okay, so let's start off with this. We want to find the 6 trigonometric functions of the angle theta, which is up here. And so far we have 5 and we have 12. We need to find the length of the hypotenuse. So how do you find the third side when you only have 2? You're going to have to do your Pythagorean theorem. So that's going to be 5 squared plus 12 squared is going to equal the hypotenuse squared. I don't know how much of your Pythagorean triples you remember, but this is 25 plus 144, which equals 169. And if I take the square root of both sides, we find that the hypotenuse here is going to be 13. So it's a 5, 12, 13 right triangle. Okay, now the other thing I recommend is if you have this one angle, because sine, cosine, all your trig functions are relative to that angle, on the inside of your triangle, I would write, so 12 is actually opposite now theta. 5, the side with the 5, is the adjacent, and our hypotenuse is over here. So I like to put a little OAH for what each side represents. All right, so now we can read off our ratios. The sine of theta is, again, remember, the opposite over the hypotenuse. So that's going to be 12 over 13. And then immediately I would do the cosecant of theta. That's going to be 13 over 12. So notice that anyone that has a hypotenuse in the denominator, that ratio is always going to be less than 1. Anyone that has a hypotenuse in the numerator, because the hypotenuse is always the longest side of your triangle, that'll always be greater than 1. So now we go to cosine. The cosine of theta is the adjacent over the hypotenuse, so that's going to be 5 over 13. And that means the secant will be the reciprocal of that, so that'll be 13 over 5. And lastly, we have the tangent. So remember, tangent is opposite over adjacent, so that's going to be 12 over 5. And the cotangent will be the reciprocal of that, 5 over 12. All right, so once you know all 3 sides, you can find those different ratios of each side. Now, let's take away some of that information and see how we solve this puzzle. Find the other trig ratios given theta is an acute angle and sine theta equals 2/3. So given a problem like this, the first thing you want to do is draw a triangle. So I'm going to draw a triangle, and I'm going to put my theta right here. You can put theta wherever you want. Now it did tell me that the sine of theta is 2/3. So remember, sine represents opposite over hypotenuse. So in my triangle, I know that this will be the opposite, this will be the adjacent, that's the right angle, so that's the hypotenuse. So I can label my opposite as 2, my hypotenuse is 3, and I still need to find the adjacent. So again, we go to our Pythagorean theorem. I'll do it right underneath the other one. In this case, I know that 2 squared plus my adjacent side squared has to equal 3 squared. So that means the adjacent side is going to equal 9 minus 4, which is 5. But we want just a, not a squared. So this is going to be the square root of 5. All right. Now, to find all 6, what I always do is write them all down right at one time. So sine, cosine, tangent. Then right next to them, you're going to write cosecant theta, and then secant theta, and cotangent theta. So if you always write them out each time, it also helps remember which one is the reciprocal of which function. So we have sine, which they gave us as 2/3. We don't even have to figure that one out. So we know the cosecant will be the reciprocal of that. Now let's go to the cosine. So looking at theta, cosine is adjacent over hypotenuse, so that's going to be rad 5 over 3. Secant then is going to be 3 over the square root of 5. And we're going to talk about that in a sec. I seem to have run out of space right here. You're going to have to rationalize your denominators. So let me finish this up and then we'll go back and rationalize. Our tangent is going to be the opposite over the adjacent, so that's going to be 2 over rad 5. And cotangent then is the reciprocal of that, rad 5 over 2. So we have two functions here that need their denominators rationalized. I don't know if you remember how to do that, so I'm going to do it on the tangent one here. Since we have a square root of 5 in the denominator, you're not allowed a radical in the denominator, so I'm going to multiply top and bottom by rad 5. Basically, I'm multiplying by 1, so I'm not changing the value of it. But by doing that, what I get on top is 2 rad 5, and when you multiply a radical times itself, basically the square root cancels out, because you would have the square root of 25, which we know is 5. And that is an acceptable answer. I know it's just as ugly, but that's kind of the process that we have to go through. So for the secant up here, I'm going to do it down here. We had 3 over the square root of 5, so we multiply top and bottom by rad 5, and the final answer is 3 rad 5 over 5. As you do these enough, you'll notice there are some shortcuts. Basically, the radical goes upstairs, and the number under the radical stays downstairs, which is kind of a quick shortcut for rationalizing your denominator. Okay, now let's get into using your calculator, because we want to figure out what some of these thetas are, or how do I know what the angle is between those two sides. That means you need a calculator. So we're going to start off with the simple one. So if you don't have one, you might want to pause the video, go get your calculator, make sure it's in degree mode, and you'll know whether it is or not, because you want to find a row of keys that say sine, cosine, tan. So obviously it needs to be a scientific. And if I hit sine, I'm going to actually just hit the key that says sine. Then I'm going to enter 36. And then I'm going to hit enter. So for equals, you're hitting enter. And if you're in degree mode, it should give you 0.588. So always try and give us 3 decimal places. That kind of helps with any round off error. And you can round to that 3rd place. So 0.588. If you didn't get that, it means you might not be in the right mode. So look and see if you can, if you just Google putting your calculator in degree mode, you should be able to find something. I'm sorry that I can't. You can email me and we can try and do a Zoom thing to help you with that. So tan 78, again, I'm going to hit my tan button and then 78, enter. And you should get 4.705 if we round up. Okay, so that's really nice. Sine, cosine, tan, you have that button on your calculator, but we don't have cosecant, secant, and cotangent. So because these are reciprocal functions, but it's the ratio that is a reciprocal, here's how you would have to figure this out. So we know if I hit sine 30, it's not a bad idea, just go ahead on your calculator, sine 30, enter, you should get 0.5, which is 1/2. All right, what if I want to find cosecant of 30? Well, so I can just do a reciprocal. The way you do that, remember, reciprocal means 1 divided by whatever that is. So I can just go, I'm going to enter on my calculator, 1 divided by sine 30, enter. And hopefully it gives you 2, because the reciprocal of 1/2 is 2. All right, so let's try this out. So that's why you need to know your reciprocal functions as well. Cotangent is the reciprocal of tangent. So I'm going to enter on my calculator 1 divided by tan 78. And that gives me 0.213. All right, so I'm trying to go through these. You should definitely try these to make sure you're entering it right and know how to enter it, because these are kind of sort of the foundation skills going forward. If I want to find the secant of 12 degrees, secant is the reciprocal of cosine. So I'll go 1 divided by cosine 12 degrees. So on the calculator, 1 divided by cosine 12, enter. And you should get 1.022. Okay? And again, I'm going to hold a Zoom session after this so that you guys can ask me any questions or anything you weren't sure about. Okay, now at the bottom here, you also did these last year in geometry. Angle of elevation, angle of depression. Remember, we also then went out to the pool and did that whole law of sines and cosines, which is our next lesson. So there'll be a lot of overlap here, which is kind of nice. So just a reminder, when you are, angle of depression and angle of elevation is also relative to where you are standing. So I have this diagram here. If I'm standing on top of a building, so let's say this is a building, and I'm looking down at the ground, so let's say my doggy is down here, so I'm going to draw a little picture of my dog. I'm looking down at my dog. Notice there's this right triangle that is kind of made. This is my line of sight. This is the side of the building. So this is the building. The angle my eyes go through to look at the dog are not inside, my eyes are not, yeah, you know what I mean. It's not inside the triangle. So I don't know how much geometry you remember, but I don't know if you remember alternate interior angles. So these are parallel lines right here, which means this angle of depression is the same as the angle of elevation, which is really helpful because the angle of elevation is inside the triangle, so I can use that angle to find, say, how far away my dog is or how tall the building is. So again, I want to emphasize that angle of depression is not, based on this diagram, it's not inside the triangle, so do not draw it in here. It's the angle your eyes go through if you're looking straight ahead on the horizon. It's the angle your eyes go through to look at their target. Okay, so let's see how this plays out in a problem. So we have an airplane that is flying along, it's going in this direction. And at a certain time, and it's flying at a constant altitude of 12,000 meters. And the pilot is looking back at the airport tower, or somebody in the plane is looking back at the airport tower and notices, because they have a handy dandy protractor on them, like we all carry those around, right? 32 degrees right there. Again, that's an angle of depression. So right away, we know that this angle down here is also going to be 32 degrees because those are alternate interior angles. All right, we want to find how far away the plane is at this moment in time when that angle is 32 degrees. So we have our right triangle set up. We have the angle that is our angle of attention, which is this 32 degrees. That makes my 12,000 the opposite, and what I'm trying to find, the adjacent. So which trig does a ratio of opposite and adjacent? So if you look up on top, you see that that's your TOA. Your tangent is opposite over adjacent. So we set up the equation. The tangent of the angle, in this case we're going to actually put in the angle measurement, 32 degrees, that's your equals, the opposite, which is 12,000 meters, over the adjacent, which is our unknown. All right, so that's how we set up our equation. It's always the tangent of an angle, you have to have a measure in there, is equals, and then you write your ratio, 12,000 over our unknown. Now notice here my unknown is in the denominator. That makes this a little trickier to solve, though you did do these in geometry. So remember, I can multiply both sides by x. That'll bring it out of the denominator. And then I'm going to divide both sides by tan 32. So I end up with 12,000 divided by tangent 32. So how did I do that? I multiplied by x, so it canceled it on that side, and I divided by tan 32, which moved it down to that side. Basically, your unknown and that trig switch positions. Now I just go to my handy dandy calculadora and I actually enter all at one time 12,000 divided by, because that's what this fraction bar means, tan 32, enter. Enter! And you should get 19,204.014 meters, since they gave us units. All right, so that's how you would handle a word problem with an angle of depression or an angle of elevation. So now we're going to do a little review of your special triangles from last year, your 45, 45, and 30, 60, 90 right triangles, because they also have some very common trig values associated with them. Believe it or not, at the end of this chapter, you're going to have these memorized, whether you want to or not, because we're going to make you. Okay, but it is the kind of thing that you just want to do anyway as you're going along. So let's go back through how you derive these special triangles. So if I have a 45, 45, we know two of the sides are the same, right? Because the opposite side is related to the opposite angle. And so they have two angles that are the same. So I'm going to call each one of these 1, because that's the easiest number I can assign to a side. So if those are each a length of 1, what is the length of the hypotenuse? Well, again, I can go 1 squared plus 1 squared. 1 plus 1 is 2, which makes that side the square root of 2. So now that I have all three sides of my triangle labeled, I'm going to choose one of these 45s as my reference angle. That makes this the opposite, makes this the adjacent, makes this the hypotenuse. And now I'm going to write down my ratio. So the sine of 45 is the opposite over the hypotenuse, which is 1 over the square root of 2, which we have to rationalize. So the rad 2 goes upstairs, and the number just drops down. That's that shortcut I was talking about. The radical will always go up because you're multiplying top and bottom by rad 2. And then that 2 just kind of drops down. Now, the reason why I like to write it both ways is because when you go to do the reciprocal, you might as well go off of the first version, which is then just rad 2 over 1. Otherwise, you're going to have to rationalize again. Now, cosine is basically the same. Cosine is going to be the adjacent over the hypotenuse, but the adjacent and opposite are the same, so you also get 1 over rad 2, which becomes rad 2 over 2. So the reciprocal will also then just be square root of 2. You want to pull it from the first one. It's easier to take that reciprocal. And then my tangent, this is the really nice thing, tangent is opposite over adjacent, and opposite over adjacent is just 1, and the reciprocal of 1 is 1. So there's your trig, your 6 trig values for an isosceles right triangle. Now we're going to look at a 30, 60, 90. So we actually have two different angles that we're going to consider. We're going to start with the 30-degree angle. Now we have nothing on any of the sides. So I'm going to go back over how you get the relationship in a 30, 60, 90. So I'm going to draw down here a equilateral triangle. So we know all sides are the same. That also then means 180 divided by 3 gives me all of these are going to be 60 degrees. Then what we're going to do, and I'm going to label each side as a length of 2 because it's a nice even number. The reason why I'm doing that is because now I'm going to cut it in half because I really only care about half of this triangle. So that makes this angle up here 30 degrees. Well, it also then splits this side into 1 and 1. So what do I have so far? I have this side is 1, this side was 2, this was our 60 degrees, this was our 30 degrees. We still need to find the length of that side. So 1 squared plus the opposite squared equals 2 squared. So the opposite squared is going to be 4 minus 1, and then we take the square root of that. All right, so notice opposite the 30 is the smallest side, it gets a 1. The middle 60 degrees is root 3, which is about 1.4, I think. And 90 gets 2. So its smallest side gets the smallest ratio opposite, biggest side gets the biggest ratio. So when I come over here to my 30, 60, 90, opposite the 30 is a 1, opposite the 60 is a rad 3, opposite the 90 is a 2. Those are the same ratios you guys worked with last year. So now we go to do our ratios. So sine of 30, that's going to be opposite over hypotenuse. So that's going to be a 1/2. The reciprocal of that is 2 over 1, or just 2. Cosine of 30 is going to be, again, so this is opposite, that's your adjacent, that's your hypotenuse, because we're working on the 30-degree angle. That's going to be square root of 3 over 2. So secant will be 2 over rad 3. So we have to rationalize that. So the 2 is already there. The rad 3 goes upstairs, and the 3 just drops down by itself. Now tangent of 30 is opposite over adjacent, so that's 1 over rad 3, which we rationalize to rad 3 over 3. And then we pull off the reciprocal as just rad 3. So there are your trig relationships for a 30-degree angle, but we need to now do the 60-degree. So I'm going to erase our opposite stuff, and now if our reference angle, sorry, I should have also erased that. So now we're going to use our 60-degree as the reference angle. That's going to switch everything up, but very nicely, because it's still the same triangle. So when I do the sine of 60, this is now the opposite. This is the adjacent. This is the hypotenuse. So that's going to be rad 3 over 2. Notice the sine of 60 is the same as the cosine of 30, because you're just switching where you were standing. So this will become 2 over rad 3, which we can notice from up here becomes 2 rad 3 over 3. Cosine now is adjacent over hypotenuse, which is 1/2. So secant will be the reciprocal of 2. Tangent of 60 is opposite over adjacent, so that's just rad 3, but the cosine will be the reciprocal, 1 over rad 3, which becomes, just like we had here, rad 3 over 3. Okay, now, as we move forward, anytime you have a 30, 60, 90, or a 45, 45 triangle, we do not want you to use a calculator. Obviously, you're going to do what you're going to do, but we don't want decimals. So you need to know the ratios, because these have nice exact ratios. That's why they're called special triangles. Whereas if I just gave you a 40-degree angle, you're going to get a decimal. You're not going to get a nice number. So how will this work? In this triangle down here, in this example, we have a 30-degree angle. We want to know what is the length of this side that is adjacent, but they gave us the hypotenuse is 8. So you want to think about, okay, we have the adjacent and a hypotenuse. What trig goes with that? Well, that's cosine, because remember, it's so, ka, toa. So the AH represents adjacent and hypotenuse. So I'm going to write out a little ratio here. The cosine of 30 degrees is the adjacent over the hypotenuse. Well, we want to solve for x, so I multiply both sides by 8, and I have 8 times the cosine of 30. Well, what is that? 8 times the cosine of a 30-degree angle is rad 3 over 2. And again, you can find that right here. So when I simplify that, this becomes, so 2 goes into 8 4 times. X is going to represent 4 rad 3. That's going to be your answer. Now, that's one way to do it. There is a second way to do this. And so this might be more how you did it in geometry. If I gave you the triangle, and we know this is 30 degrees, you know this is 8, this is what you're looking for. Well, you have that relationship that opposite the 30 is always going to be half as long as the hypotenuse because we split the triangle in half. So notice my side opposite 30 is half the hypotenuse. So the side opposite my 30 I know is going to be 4. And you guys probably did this last year. You wrote inside the relationship, that's x. This is 2x. This is x rad 3. So it's all based on whatever your 30 degree is, you double it to get your hypotenuse, and you multiply by rad 3 to find what is on the 60 degree side, because that means this is 60 here. And so notice we got the same answer, 4 rad 3. So 2 ways to do the same problem. All right? I hope this helped.